So this is a reminder, Class Connect sessions are recorded and distributed for learning purposes that are listed here. As always, be respectful, appropriate, and participate. Please don't share personal information such as contact info during class for your own security reasons. All right, so sorry, we're going to go ahead and skip this one because we have a lot of stuff to go through today, but let's go ahead and make sure we have our attendance check open and ready to go. You filled out the word silver already for your start of class word. Waiting on a green check from Alejandra, Alicia, Ari, Brandon. Green checks, please. David, Estella, Jelly, Hannah, Jorge. Green checks, please. Micaiah. Hi, David S. Welcome to class. Here's your link, and the start of class word is underneath there. Perfect. All right. Make sure you give me red X's if you ever run into issues with that, but let's go ahead and keep on going. All right, everyone. So there are only 19 days left of the quarter and therefore of this course. So courses will end in 19 school days, and that means that you won't be able to submit anything after this day. So make sure you are on top of all of your work because it's ending really, really fast. We are already in Unit 6. So today we're talking about work and power, two really important physics concepts. So that's what we are taking a look at today. Don't forget that your lab was due yesterday, and this is the easiest lab in the entire course. So please make sure you get it done. Remember, I do the entire lab in front of you in the recording. So make sure you watch the recording and get the data as I do the lab in front of you. All right, give me a smiley face, everyone, if that makes sense, where we're at, as well as about the lab. Awesome. All right, everyone. So here we go. We are in Unit 6, which is all about work. So work and the ability to do work are the focus of our unit. We will take a look at what are called simple machines. You can see some of them over here that you might be familiar with, like a seesaw, also called a lever, or a screw, or a pulley. Those are all examples of simple machines, and the factors that influence force. And we will again also take a look at pulleys and levers. All right, so that's what we're going for this unit. Today, though, we first need to learn a little bit of background. So we need to talk about what are the various types of work, and we should be able to calculate work, and we should also be able to describe what power is and how that is related and different from work. Okay, so at this point, I'm going to go ahead and send out your notes. All right, so please make sure that you open up your notes or you are ready to take pictures or screenshots, and then give me a green check once you're ready with that. So green checks if you have your notes open or you're ready to take pictures. Keep on getting me those green checks. I will be right back. Hold on. All right, looking good, everyone. Oh, okay. Yeah, sorry about that. Sorry, our dates are a little bit off because I was out a couple days last week. Let me go ahead and I will fix that. Thanks for letting me know. Yep, no worries. All right. Perfect. Thank you. All right, everyone, looking good. Let's go ahead and keep on moving here. So we are talking about energy and work today. All right, so we've talked a little bit about energy already. We're now going to talk about how work is related to that. So first things first, grab your polling tools, and I want to know the lines in the picture number 1. Are these parallel, perpendicular, or neither? Let's go ahead and think back to what we know about parallel versus perpendicular lines. What do you think these are? Use your polling tools really quickly. Go, go, go. I got an answer from David S. I got an answer from Jarrett, from Janice. So these lines right here, are they parallel or perpendicular? There we go, getting some more answers. Thank you, Chris. Thank you, David M. All right, waiting on some more participation. Keep in mind today that I do have an MIA room just because it's really exhausting to say names over and over again. So if I feel like you might be falling behind and you need some help, you might get moved to that room so I can check in with you. All right, looks like most of us are saying C. It is actually not C. All right, so go ahead. I'm going to clear these out. C is not one of the options. Let's go ahead and figure it out now. All right, if C is not one of the options, is this parallel or perpendicular? Parallel or perpendicular? Try again, try again. It is one of them. It's either parallel or it's perpendicular. Good. All right. So it looks like we are coming to an agreement. Yes, this is actually perpendicular. So perpendicular lines, remember, mean that there's a 90-degree angle between them, right? So they intersect each other kind of halfway through. Smiley faces if that makes sense. So when they intersect each other and there's a right angle, that is a perpendicular line. Awesome. So that being said, let's go ahead, clear these out. And now take a look at number 2. What are these lines? What are these lines? Use your polling tools and tell me, what are these lines? the red lines here. Are they parallel A, perpendicular B, or neither C? I know, it is early, right, David? I feel your pain, don't worry. All right, thank you, Jarrett, got your answer. Thank you, David, Chris got your answers. Taja, Micaiah, Nichelle. Perfect. Looks like we're saying A for those of us that are answering, and that is true. These lines are parallel, and the reason that they're parallel is they could continue on forever and they will never touch. So always think about parallel lines just means that they're so next to each other, they're so lined up that they could continue forever and ever and never touch or cross each other. Okay, so that being said, let's go ahead and take a look at our last one. The lines in this picture, are they parallel, perpendicular, or neither? What do you think? Oh, I can't even trick you guys. Yes. So these ones are actually also parallel because even though they're slanted, it's still true that if these lines were to continue going forever, they would never actually cross or touch each other. Give me a smiley face if that makes sense. So I can even show you. If we continue these lines on forever and ever, they still will never cross, never touch. Awesome. Okay, so why is that important? That has to do with our topic for today. So going back to talking about energy, remember potential energy is the potential to be able to do something. So it's stored ability to do work. No worries, Ari. So for the 4D exam, if you need help, I have a office hours on Wednesday and Friday that you can come to and I can help you with those. Okay, let me know if the time doesn't work for you. It should already be on your schedule, but if it doesn't work for you, you can email me and we can set up a different time. Okay. Now, kinetic energy, on the other hand, we've talked about kinetic is motion. So kinetic energy is things become kinetic energy when work is being done. So potential is the stored ability to do work. Kinetic energy is when work is actually being done and things are moving and changing and there's motion, right? So for example, when you lift something against gravity, the potential energy is the stored energy, but when you're lifting it, it's becoming kinetic energy and moving. Okay, give me a thumbs up if that's beginning to make sense. All right, so we're talking a little bit about potential versus kinetic. Okay, so that being said, what is work? The way that we understand work is when a force, any force, which is a push or a pull, on an object causes a parallel displacement. And another way to say displacement is a motion or movement. Okay, so when a force causes something to move in the parallel direction. Now that could be the same direction, right? If something's going to the left, if your force is going to the left, then the direction could also be the left, or it could be the opposite, but still parallel. So what's the opposite of left, but still parallel? What direction is the opposite of left, but still parallel? Tell me in the chat box, right? So things could be going, your force could go to the left and your object could go to the left, or your force could go to the left, but your object's going the opposite direction. Tell me in the chat box, what's the opposite direction? Yeah, to the right, exactly, Nichelle. So those are still parallel though. So their work is still being done even if the object is currently moving in the opposite direction. So this is like if you have a soccer ball coming towards you, right? But you're trying to force it to go away from you. Okay, give me a thumbs up if that makes sense. You still have to do work even if the object is moving towards you. Okay, so for example, when you lift something up off of the ground, the displacement, its motion is parallel to the force. So when we're lifting, which way is our force going? Tell me in the chat box. When we're lifting, which way is the force going? Yes, so your force goes up. And when these boxes are being lifted, which direction are the boxes moving? So your force is up, but also which direction are the boxes moving? Yeah, the boxes are also moving up. So your displacement, the motion is also upwards. So those are parallel. And so work is being done. So work, yes, star, it's being done. Awesome. This is number 1 in your notes. Go ahead and fill in the blank with the word displacement. You have 30 seconds to either get that done or take a picture. Ready, set. Waiting on a green check from Alejandra, Brandon, Estella, Sean, Shelby, Susan, Travis. Green checks, please. All right, let's keep on going. All right, so that being said, we understand what work is, right? When a force causes a displacement that's parallel, either in the same direction or the opposite direction. But the actual equation is that work equals force times distance. So work is whatever force you have times the distance. So the amount of applied force, the distance that the object is displaced or moved. And again, we're only looking at what's parallel. So we're only looking at if the parallel force and the displacement that's parallel to it, that's what gets multiplied together, okay? If there's ever anything that's not parallel to the force, then that does not get multiplied together, okay? Give me a thumbs up if that makes sense. That's why we went over this idea of parallel versus perpendicular. It matters if things are parallel. Excellent. Fill in the blank with the word force. Give me a green check. You have 30 seconds. This is a really fast one. Go, go, go. 3 seconds. Green checks, please. Good. Waiting on a green check from Alejandra, Ari, Chris, Danny, Jorge, Sean, Susan. Green checks, please, for number 2. Fill in the blank with the word force. Awesome. Moving on. All right, so that being said, work is the work done on or by an object is worked out using the equation work equals force times distance. We're going to learn that the units for work are joules. Force, we already know the units are newtons, and distance, the units are meters. Okay, so let's go ahead and do an example. So a person pushes a box 15 meters along the ground using a force of 100 newtons. How much work has been done? So first we need to figure out, are these parallel? Okay, so the person is pushing the box to the right, and the object is moving 15 meters to the right. Is that parallel? Yes or no? Is that parallel? Yeah, so the force is to the right, and the distance is also to the right. So those are parallel, so we do know that work is being done. So those are parallel, so work is done. All right, perfect. So now that we know that, let's go ahead and actually plug this in. So again, work equals force times distance. What was the force in our problem? Take a look at our problem here. What was the force used on the box? What was the force used on the box? Remember, we're looking for a number that ends in newtons. Yeah, 100 newtons. So 100 newtons right here is our force. So that's what we're going to fill in for our first blank. So work equals 100 newtons times, what's our distance? Take a look, annotate your problem here. What is our distance that the box moved? Yes, so remember meters tells us that that's a measurement for distance. So I'm going to use what's next to meters, which is the number 15. So this is our distance, so times 15 meters. And plug that into a calculator or do some mental math and tell me, what is 100 times 15? What is 100 times 15? Excellent. All right, I'm getting some numbers. They're looking good, but I also want to make sure that you're including the units. Remember, I said the units for work are joules. So what does the work equal, including the units for J for joules? Yes, awesome, Nichelle. Awesome, Landon. Thank you, Janice. Yes, so 100 times 15 is going to give me 1,500. And the units, again, are joules, so I'm going to include a J to show joules. All right, give me a smiley face if you're feeling comfortable with this. It's a pretty easy equation. Just take your force and distance, multiply them together, as long as they're parallel. They must be parallel. Perfect. All right, you guys are so good at math, right? All right, so work equals force times distance. Again, the unit is joules, and joules is actually just a long name for newtons times meters, okay? So let's go ahead and take a look at an example here. So we have a 1 kilogram object, all right? So what we need to do is we need to figure out what is the force due to gravity on a 1 kilogram object. So the force due to gravity, remember, equals the mass of the object times the acceleration due to gravity on the object. Okay, so take a look here. This object is 1 kilogram. Is that the mass or the acceleration? Tell me in the chat box. Is that the mass or the acceleration? Yeah, 1 kilogram tells us the mass, right? So this is 1 kilogram times the acceleration due to gravity on Earth. Do we remember what that is? What is the acceleration due to gravity on Earth? All right, so the acceleration due to gravity on Earth is 9.8 meters per second squared. 9.8 meters per second squared. So what do I get when I multiply 1 kilogram times 9.8 meters per second squared? Tell me in the chat box. What's 1 times 9.8? What is 1 times 9.8? Yeah, easy peasy. It's 9.8. But this is going to tell us the newtons or the force or the weight, force or weight of the object. Okay, so that being said, this object that's 1 kilogram, the force that we need to lift it up is going to be the weight of the object. So the force or weight of the object we said was 9.8, what's going on here? Was 9.8 newtons. Give me a smiley face if that makes sense. Okay, so that's where they're getting this force or weight that we need in order to lift the object is 9.8 newtons. Okay, so a 1 kilogram object on Earth has a weight of 9.8. So in order to lift it, we need 9.8 newtons of applied force. So now depending on the distance that you lift it parallel to working against gravity, that is going to show us our work. So let me go ahead and pull this up. All right. Give me a thumbs up once you can see my screen. All right, so you actually have access to these additional reading materials at any time. They're optional, so you don't have to look at them if you don't want to. But there are some interesting things that you can play around with inside of them. So if you ever want to take a look at them, plus they have good information that covers other stuff that we don't always go over. Okay, but let's take a look at this one right here. Let me blow this up for us. All right, so take a look at this object. Again, the object, the force we need to lift this object, we already calculated, is 9.8 newtons, okay? Yeah, it'll be choppy until I slow down, so I just stopped it, so hopefully it shouldn't be too choppy. Now, it hasn't moved at all from the ground, right? So if it hasn't moved, how much work do you see have we done? If we haven't moved it from the ground at all, how much work have we done? 0, right? It's 0 meters from the ground, and anything times 0 means 0 work. Awesome. Now, if I go to the next slide, and you can see at this point, we've lifted it half a meter up. So now we have the 9.8 newtons that we're pulling it up, as well as it moved up parallel to it, 0.5 meters. Now, what's the amount of work that we've done? Take a look at our screen here. Excellent. Yes, Nichelle. So we've done 4.9 joules of work at this point. And then what do you think is going to happen when I lift it up to 1 meter? What do you think is going to happen when our distance changes to 1 meter? Tell me in the chat box, right? So 0 meters, 0 work, half a meter, 4.9 joules. What do you think is going to happen when we have 1 whole meter? When I change this number to a 1, how much work will we get? I can write it out. 9.8 newtons times 1 meter is going to equal what? Awesome. I see Johnny's typing. I see Jarrett typing. Kimberly. Yeah, it's going to give us 9.8 joules. So we can see the higher up we go in parallel the motion, the higher the work goes, right? So now it's 9.8 joules. Smiley faces if that's beginning to make sense. Okay, so the more you move it, the more work is done on the object as long as that motion is parallel. Perfect. Okay, so let's jump back over here. Looking good. All right, so let's go ahead and do a problem here. So we want to calculate the work done on a wagon if we push it 35 meters with a force of 50 newtons. So first, let's annotate this. 35 meters, what is that telling me? Is that telling me work, force, or distance? 35 meters, is that telling me work, force, or distance? Yes, this is going to be our distance, right? So I'm going to annotate this with a D to tell me that's the distance, and I'll show that that's where it's going to get plugged in. And 50 newtons, what does that tell me? Newtons is the units for what? Yes, this is the units for force, absolutely, so that will get plugged in here. And then what am I trying to solve for here? Always try to think about what is your answer that you're looking for. Joules would be the units, right? But we're solving for work, right? So we're trying to solve work equals what? What is work? Okay, so that should help us plug this in. Do you guys want help plugging this in, or do you think you can do it on your own? Do you want me to write it out, or do you think you can do it on your own? All right, looks like we're doing it. So, okay, grab your polling tools. Tell me, what answer do you get? What answer did you get? Sounds like we're pretty confident. Yep, so plug in force, multiply it by the distance you plugged in, and that should give us our work. Looking good. Need lots of participation. I have 6 answers so far. There are 28 of you, so I need way more answers. Everybody's participating. I want to make sure I'm not leaving anybody behind and that we're all working together. So we're supporting our classmates by working together, making sure that we're pulling our own weight. Awesome. Looking good, looking good. All right, I have 10 answers, still 28 of you, so I'm still waiting on some answers. Let's see here. Elena, Alejandra, Alicia, Chris, Danny, David, Donnie, Estella, Jelly, Jarrett, Jorge, Lorelei, Sean, Susan, Travis, Green. Go ahead, get me your answers. Looking good. All right, let me go ahead and publish these up on the board and clear these out. And it looks like most of us are saying D, and that is actually correct. All right, so let's go ahead and check our work in case anyone is uncertain about how we got that. So again, work is what we're solving for, so we leave it as the W. Force, we know what force is. That was 50 newtons. Times our distance, we know what distance is up here. That was our 35 newtons. And so when you plug that in, 50 times 35 gives us 1,750, and the units again for work are joules. Give me a smiley face if you feel good about that. Again, this equation is not very difficult. We should be able to work on that. No worries, Ari. I know math can be intimidating. That's why we're working on it together. And that's why we're doing multiple practices. Right? So always just remember you're plugging in force where it goes, you're plugging in distance where it goes, you multiply them together. Don't worry, Ari. There's lots of opportunities for practice. Hi, Aqua. Good to see you. Oh, no. That's so sad. I'm sorry, Alicia. It's okay. Just jump on in with your notes, and anything that you missed, it will be in the recording. Okay? All right, so that being said, when a force is perpendicular, remember we talked about how parallel means the lines never touch, right? They go in the same direction or the opposite direction, but they never touch, okay? So parallel, we know what that is. However, when they are perpendicular, meaning that they're at right angles to each other, then no work is done whatsoever, okay? There is no work done. So for example, if you are applying a force vertically against gravity, okay, so let's say that I am lifting up this book vertically against gravity, okay? But I'm walking horizontally, okay? So my displacement or my movement is horizontal, then there is actually no work done, which is kind of sad, right? Because you could be lifting a really heavy weight above your head, but if you're walking horizontally, you're not actually doing any scientific work, right? Which is a little bit sad. Okay, so if your force is upwards, like you can see here, this person's lifting this box up, but they're moving to the right. Moving to the right is a perpendicular motion, and so there is no work done here. Give me a thumbs up if that's making sense. No matter how far this person moves, there will never be any work done on this box if it's perpendicular or horizontal, not parallel. Okay? So yes, it's not work. All right, go ahead and fill in the blank here with the word perpendicular. Give me a green check. You have 30 seconds. Go. Or you can take a picture. Oh, okay, green checks, please. Alejandra, Chris, Danny, David M., Donnie, Estella, Jorge, Micaiah, Sean, Susan, green checks, please, for number 3. And we're moving on. All right, so overall, based on everything that we've learned so far, there are 3 elements that are needed for work. We need a force, because our equation includes force. We need a displacement, or a motion that's parallel to the direction of the force. So it has to move a certain distance that's parallel. And it needs to cause one another, right? So the applied force must cause the actual motion or displacement. So they have to actually be related to each other in order for this to be considered work. Okay, thumbs up if that makes sense. So you need these 3 elements to happen in order for this to be considered work. Okay, so let's go ahead and take a look at whether or not work is done in these different scenarios. So take a look down here. So this person is applying a force to this box to the right, and the distance the box is moving is 0 meters. So is work done here, yes or no? Tell me in the chat box. If the person's pushing to the right, the box moves 0 meters, is work being done? No, and why is work not being done? Tell me in the chat box. Why is work not being done? Which part of our 3 elements does this not apply? Or does this not fulfill? Which part of our 3 elements here does this scenario not fulfill? Yeah, there's actually 2, right? So first off, there's no displacement, right? So number 2, there's no displacement. And number 3, the force is not causing any displacement. So both of those are true, all right? So the force is not causing a displacement, and there's just no displacement in general. So that is why there is no work here. What about for our skier here? So we have a force going to the right, and the person is moving to the right. Is work being done here? Yes or no? Is work being done? All right, so we're saying yes or no, yes or no. Is work being done? Force is to the right, direction is to the right, displacement is to the right. Yes, there is definitely work being done here because we can see, right, there is a force. So number 1, check. There is a displacement, check. And they are parallel, right? So that's almost a double check. They are parallel and they're causing one another, right? The force to the right is actually causing the object to move to the right. So check that one as well. Excellent. All right, what about the top one? So the top one, we have someone who has a force that's pushing upwards on this box, and he's walking to the right. So the force is going upwards, and the displacement's going to the right. Is there work being done here? Is there work being done here? Okay, so let's take a look at this. We have a force, right? So number 1, we have a force. Number 2, we have a displacement, or a motion. Is it parallel to the direction of the force? Is the displacement parallel or in the same or opposite direction of the force? No, yes, we just did this with the book. So this is not work. This is actually not work because these are perpendicular to each other. Anytime something is perpendicular, there is no work. Give me a smiley face if that makes sense. That's why we do these checks, so that we can correct our misunderstandings. That's how we learn. Yeah, don't worry. That's how you learn. Awesome. All right, so this is number 4. Fill in the blank with the word cause. Give me a green check when you have that saved or you've taken a picture. Go, go, go. All right, waiting on green checks from Alejandra, Alicia, Chris, Danny, David, Donnie, Jorge, and Micaiah, Sean, Susan. Yeah, I know, Aqua. Seems like there's some lag going on. I'm sorry. All right, looking good. Sean, Susan, are you there? Hello? Sean, Susan, green checks, please. Jorge, you as well, green checks. Danny, still waiting on you. Alicia, Alejandra, are you there? Okay, you did it. Awesome, Alicia. Thank you. All right, perfect. All right, so let's go ahead and keep on moving. So now we're going to go ahead and talk a little bit about our next one. And our next one is all about power, okay? So power is actually related to work, but it's also related to the time it takes to do the work, okay? So work and power are related, but they are not the same thing. So work we talked about is when an applied force, right? So this is when an applied force, sorry, one second, displaces or moves an object. But power is actually the rate at which this work is done over time. So work is what is happening, but the power is the actual time it takes to do it, okay? So for example, a powerful lineman, all right, lineman, is both strong, meaning he can apply a big force and do a lot of work, but he's also fast, meaning he can do it in a very quick amount of time, a very small amount of time. So for example, would a lineman be good if he was strong, but really, really slow? Tell me in the chat box, would he be a powerful lineman if he was strong and could do a lot of work, but he did it very slowly? Would that be useful in a football game? Linebacker, yeah. Right, so you want to be strong, so you can do a lot of work. But what would happen if he was slow? What would happen if he was slow? Would that be useful if he was slow? If he just like walked the field? No, it would not be useful. So he has to be both strong and fast. So strong means he can do a lot of work, but fast means he can do it, he has a lot of power. Has a lot of power, can do it fast. Can do it in a small amount of time. Give me a smiley face if that makes sense. Right. I know he doesn't need to run Aqua, but he still needs to like be quick about it. He can't just like move at the speed of molasses. That doesn't work, right? If he just stays there for a really long time and doesn't move, it doesn't matter how much work he does, his power will never be very good. Okay, so fill in number 5 with the word not. Give me a green check. You have 30 seconds. Go, go, go. All right, waiting on green checks from David M, David S, Donnie, Aqua, Jelly, Taja, Susan, Travis. Oh, did you, David? Cool. And I imagine if you were really, really slow, it wouldn't mean that you were a good one, right? If you're faster, I think it makes you a better one, right? Yep, perfect. All right, looking good. So power is going to be the rate that the work is actually done. So it does not matter how much work you do. If you and another person are doing the same amount of work, but someone does it faster, that person has more power, right? So power is the work divided by the time. So we've talked about work units are joules and time units are seconds. So when you do joules divided by seconds, this creates a new type of unit called watts, named after James Watt right here. So 1 watt is also 1 joule per second. So the units for power are watts. Smiley faces if that makes sense. So instead of saying joules per second, which is really long to say, scientists just say watts instead. Awesome. All right. So again, work can stay exactly the same, but the faster you do things, the more power you have. Power speeds things up. So power is both how much work you do and how fast you get it done. Okay. Same thing with like if you're studying, okay. If you and another person are studying the same work, right? You're doing the same amount of work, but one person does it in an hour and another person does it in 3 hours. The person who's going to have more power, right, might have a better grade is the person who can get it done faster, right? So even though you're doing the same amount of work, whoever does it faster has more power. This is number 6. Fill in the word rate for the blank. Give me a green check. You have 30 seconds. Go, go, go. All right, 5 seconds left. Sorry, now I'm going a little bit fast, but we still have a couple more things to get through. Awesome. Thank you. Let's keep on moving here. All right, so let's go ahead and do a scenario. Let's imagine work and power are like two people eating apple pie. Who likes apple pie? Who likes apple pie? All right. So, I mean, we could be talking about any of them, Aqua, but in general, on the field, you have to be kind of fast. You can't just be slow and doing nothing. All right. So they both eat 2 slices of pie, which means that they do the same amount of what? Tell me in the chat box. Are they doing the same amount of work or the same amount of power? If they both eat the same thing, is that work or power? Yeah, we talked about it, right? So the overall what's happening, that is work. So what's happening is they're eating pie and they both do the same amount. So that's the same work. However, one ate it much faster, which means that person that ate it faster has more what? Work or power? The person who ate it faster has more what? Yeah, exactly. They have more power. So same thing you can see down here, right? Both of these bikers are going to the top of the hill, right? But one of them does it in 30 seconds and one does it in 45 seconds. Who has more power? A or B? Which person has more power? Tell me in the chat box, A or B? Yes, person A has more power. And why do they have more power? Right? They did the same work, right? So A and B both do the same work, but why does A have more power? Yeah, they're faster. So he was faster, and so that means he has more power, whereas B was slower, and therefore he has less power, right? Which should make sense because I'm sure his legs would be sore by the time he gets up there. Good. All right, everyone. So let's go ahead and talk about how can we increase power. So in order to increase power, we need to decrease the amount of time it takes to do the same amount of work. Again, the work overall might be the same, but if you can do it in less time or faster, then you win, right? So remember, power equals work divided by time, or P equals W divided by T. So what we're going to take a look at is we're going to take a look at a high power motor versus a low power motor, and they're attached to blocks of equal mass, which means that they have to do the same exact work because the same work is lifting these blocks. However, the one with greater power should mean that they can do it in less time to do the same work of lifting the blocks. So let's go ahead and take a look at this right here. All right, thumbs up when you can see my screen. Okay, so let's go ahead and take a look at this. So I'm going to go ahead and press play. And again, they're doing the same work. They're going to be lifting the same object, the same distance, but we're going to look at the high power one on the left versus the low power one on the right and see what's the difference between them. All right, here we go. All right, what did you notice was the difference between them? I'll kind of rewind a little bit so that you can see it and blow it up, right? But what is the difference between the high power one versus the low power one? They're both lifting it up to 1.5 meters, and it's both the same object, or I guess they're both lifting it up to 1 meter. It's both the same object, but what was the difference between the one on the left and the one on the right? Now, it doesn't have to do with how fast they fall, right? They're the same object. They should hit the ground at the same time once they fall. But if you take a look at right here, what's the difference right here? We're about like 4 seconds in right now. So what's the difference between the one on the left and the one on the right 4 seconds in? It has something to do with time, but what about time? We want to be specific. Yeah, so the high power one got it up further in much less time than the low power one, right? So if I continue going to the end, right, you'll see that eventually the low power one does get it up there. However, it took a lot longer, right? It took about 6 seconds for the low power one to get up there, as opposed to the high power one, it only took about, what, 2 seconds? Smiley faces if that makes sense. Okay, so the high power one got it up in 2 seconds. The low power one only got it up in 6 seconds. It took a lot longer. Cool, so let's go ahead and actually calculate that out, okay? So we have a 1 Newton block that's lifted 1 meter in 0.25 seconds. And a 1 Newton block that's lifted 1 meter in 0.5 seconds. So again, they both have to be doing the same work. So let's plug this in. What's the force of the object? Tell me in the chat box. Look for newtons. What is the force of the object? A 1 Newton block lifted 1 meter, a 1 Newton block lifted 1 meter. What is the force there? Yeah, exactly. It's 1 Newton, right? Times the distance. And what is the distance that they move in both scenarios? Remember, work is actually the same in both scenarios. Yeah, it's 1 meter. So 1 Newton times 1 meter, what work is that? What does that give me? What's 1 times 1? 1 times 1 gives me how many joules? Yeah, 1 joule, right? So our work is 1 joule. But now what we're going to do is we're going to see a slow motor versus a fast motor. Oh, sorry, this one is the fast one. All right, so let's go ahead and plug that in, all right? So remember, power equals work divided by time. So now work for this one was 1 joule, and work for the one on the right was also 1 joule. But the one on the left only took 0.25 seconds. Plug that into a calculator and tell me what work does that give me? What power does that give me? This should be a P for power. What power does that give me? 1 joule divided by 0.25 seconds, as opposed to on the right, power equals 1 joule divided by 0.5 seconds. Yeah, so this gives me a power of 4 watts. 4 watts. Whereas on the right, what is 1 divided by 0.5? What is 1 divided by 0.5? Only 2 watts. All right, so smiley faces if that makes sense. Both of these motors did the same work, but the faster one that did it in less time is more powerful. All right, go ahead, fill in the blank with the word decrease. You have 30 seconds, and then we're going to wrap up. Go, go, go. All right, here we go. All right, everyone, so we talked about the various types of work. So we talked about work versus power. On the whiteboard, how are you feeling? Point to where you are. Confused, still need help. Pretty good, awesome. How are we feeling about today's objectives? Looking good, awesome. Looks like a lot of us are feeling really good. Love it. All right, so make sure you submit your completed 6A notes, and then I'm going to go ahead and stop our recording here.